Okay, good day to you all. My name is Abubakar, and I'm happy once again to be part of the 26th International Conference, Computational and Mathematical Methods in Science and Engineering. I'm going to be talking on a modified inexact method for non-smooth equilibrium problems. This is a joint work with Associate Professor Kanukan from Kim Mangkut University of Technology, North Bangkok, Thailand. So why equilibrium problems? Here, as we know, equilibrium problems provide a unified framework for many models in nonlinear analysis optimization. As special cases, such models can include optimization problems, variational inequality problems, fixed point problems, and models arising in economics, market equilibrium, game theory, and so on. So the equilibrium we are considering in this case is given a non-empty closed convex set K of a real Hilbert space H and a bifurcation here, big theta, with theta at zz equals to 0. The classical equilibrium problem, as we can recall, is to find a point in K such that this inequality is satisfied for all V in K. So one of the challenges of this is, as we know, it requires computational challenges, because classical projection types method for solving this kind of problems require exact projection onto some complicated physical set. And we know projection is a big deal in the sense that it's a kind of minimization problem. In a situation where you are projecting into a complicated set, that will be computational, and in some cases the project you cannot even have an exact projection to provide, unless if the set is well behaved in the sense that it has an exact projection. And also we are dealing with a non-smooth. In a non-smooth setting also, getting the exact subgradient and projection can be difficult. So also the classical, if you look at the classical equilibrium problem, the constraint, the physical set here is considered as a closed and convex. So giving it a particular structure, for instance, of fixed point, set of fixed point, solution of fixed point of some nonlinear mapping can give it more added advantage. So a practical method should allow approximation error while preserving strong convergence, as we know. So this is one of the motivations here for our proposed method. We want to propose a method that uses inexact metric projections instead of the exact ones, and likewise inexact subgradient calculations instead of the exact ones. And also we introduce momentum time, or a kind of perturbation, in order to have a faster convergence. So before I continue, I will mention some of the related literatures. Uduka here in optimization propose the following algorithm. You can see here also the constraint set for his problem is a set of some fixed point of a firmly non-expansive mapping here S. So the algorithm follows like this, where you initialize, you define a K, set K, and now you choose sequences in K such that this is satisfied, and you provide the update in this form. And where eta K here is the step size defined by this. And you can see here now the blue K now in the sub differential of the bifunctions we are dealing with at beta K at this. So here they are considering exact computation of the subgradient here. So and also another related issue, you can see Santos in Computational and Applied Mathematics 2011 proposed a method that requires, you can see here, this is the method. You choose a point in K and you compute omega K and set this value for the step size. You can see now the update here like it's simply an approximate projection instead of the using exact projection, which is approximated by epsilon here. So this is one of the key motivation we use. So we pick this kind of approximate projection instead of the exact one. And also are now considered a more generalized problem in the sense that the constraints, the feasible set here now K is a kind of a common fixed point now of some SIs here, which are the family of demi-contractive mappings. So what this is our proposed method, and what makes it different from the related ones I've mentioned. We can see here we incorporate a parallel fixed point correction structure, and also we use a partook descent direction. You can see the decay how it's defined. Here you will see when I show in the algorithm that mu k here now is a subgradient computation. In a case where you are dealing with a smooth function, you can see this is just the gradient of the function here, and you see that this perturbation incorporates the previous direction information dk minus 1, which is very important in in convergence here. It has been shown that this kind of perturbations numerically it facilitates the convergence, at least numerically. And also we use this form of step size and inexact projection method. So the main problem we consider here is this: we want to find a z star in this, where here now you can see this is the set of common fixed point set of this delta here. So we want to find such that this is the equilibrium, and now we are considering a constraint set of common fixed point of particular mappings here, beta I demi-contractive mappings. And this is just to remind the definition of the E metric here. In this sense, we are considering an minus epsilon square over 4 metric projection of z onto k here instead of the z metric. And also here the diagonals of differential also approximated by this. You can see that it allows inexact subgradient information here, and also the parameter here, or the sequence tau k here, control the subdifferential error at each iteration k. So this gives also more flexibility in the subdifferential calculation. So this is the proposed algorithm here. We choose a point z0, and for each k now from 0 1 we can for each I first we compute. This is the parallel information here. We are computing bki by this is a converse combination with alpha ki at each I. Then we select the one where the maximizers here bk, the values has the biggest distance between bki and zk. In other words, the one that most violated the fixed point component here, then we set bk to be that point, and we choose mu k here. In this, you can see this one is kind of the approximate or inexact computation of the subdifferential here. And if k is 0 at the initial point, this is a kind of a descent direction, and then this one at subsequent iteration, you can see it includes the previous information of the previous direction here. And then we set the step size k gamma k to be lambda k over theta k, where theta k is given as the maximum between some sequence rho k and the norm of dk. And the update here, you see we are using an inexact or approximate projection instead of the exact one also. So, and these are some control conditions for the sequence involved here to be satisfied in order to have control over this kind of we did not get the sequence to blow up. And you can see these are the choices of the control we put in some of them. And also, so first of all, we try to show the boundedness of this such direction that we include the direction that involves the previous direction. We were able to show that if we assume this y function to be weakly continuous for each k, and the subdifferential here is compact, then the search direction decay generated by the proposed algorithm is bounded. In other words, we can be able to have norm of decay is less than or equals to some number. So, and for the strong convergence here, we were able to show the strong convergence given that the bifunction here is a beta strongly monotone, and also the set here of the differential here is compact, and also then for each of the set we assume the SI's mapping here to be beta I demicontractive, and the control conditions holds. Those control conditions of the sequence, we assume them to hold, then the sequence generated by this proposed algorithm are bounded, and also we were able to show that this limits equals to 0, and the limit of the sequence zk is the same with the limit of the vk, which is equals to z star, and this z star happens to be the unique solution for the equilibrium problem we are considering. So for the main structure of the proof, we were trying to establish the boundedness of the generated sequence by some kind of quasi-Fourier monotonicity property. We can see where we establish also the convergence of this sequence, where we were able to use the convergence of the lambda k to establish this, and then subsequently we show that if the weak cluster point is in the solution side, and we get eventually we get the strong convergence. And as an application, a particular case where our considered problem can be treated as a variational inequality problem is if, when we define the bifunction here theta to be the same as the inner product of az with v minus z, where this az is some nonlinear mapping. So, and also remember that variational inequality problem is given by this problem that you want to find a point in K such that this inequality, this inner product is greater than or equals to 0 for all V in K. So, as we know also, variational inequality is a very important problem in which many applications have been considered, like for instance in machine learning, and a lot of applications in engineering as well, and economics. So with this we were able to derive this algorithm for solving the variational inequality problem proposed method where VKI are computed by this, and you can see also here now the direction we are now taking, instead of that subgrade we are taking minus AVK when K is 0. This is a kind of descent direction, and for the subsequent iteration, like I told you, we take this AVK plus psi k dk minus 1, and the step size is defined. And also here we are using an approximate projection here instead of an inexact projection. So, and this is the result for the convergence of our method. And for also the particular, since we can be able to show that the derived also algorithm is convergent in such a way, we have, if we assume the underlying operator here A to be B strongly monotone and L Lipschitz continuous, then for each I, and we assume this SI, we return them to be beta I demicontractive mapping, then for each one, and suppose the control assumptions are satisfied, then the sequence is generated VK ZK by the proposed algorithm here. The reduced algorithm is we can be able to say that they have the same limit, and also they converges to Z star, which is the unique solution of the variational inequality problem. For as a numerical illustration, we give two examples, one in finite dimensional problem, and in particular R5, and the other one in infinite dimensional problem. In particular, we use the big L2 spaces, that is the interspaces of integrable functions here. And these are the specification of the software. We use MATLAB for generating the code, and for simulation we use this particular processor. And all matrices here in the first example, we consider this finite dimensional case where the constraint set is given by this, and the bifunction here is given by this, where Q is defined by this with M as a matrix, N is Q matrix, S diagonal, and this Q is a vector in R5. So here we define the underlying operator A to be this, and the fixed point mappings, the demi-contractive mappings, we use two S1 and S2 given by this, and also we defined this one to be like this. And we consider the following control parameters for the proposed algorithm. We can see these control parameters, they satisfy all the properties, I mean the conditions we impose for the convergence theorem. And for the compared algorithm, here we compared with the work of An Hong, which we said published in Optimization Letters in 2021, which is considering the same problem with our problem, but with a different algorithm. So for his work also, we consider these control parameters, and we believe these choices of control parameters are the optimal choices he can choose for his algorithm in order to get an optimal performance. So here now, this is for example, the finite dimensional case. This is the convergence of the iterates generated by our proposed method. We can see that this is telling you that all the dimensions are converging to 0, and also this is the convergence against iteration. After some iteration, you see how the error now is reducing significantly at the time here. This is just to show the behavior of the proposed algorithm. And in comparison here, you see that the algorithm of An, which we call here algorithm 3.1, now we see here this one has less error and converges with less iteration than the, and here we can see now but in the times here you can see this is a trade-off. But in this case, this particular algorithm executes takes less computational time than our proposed method. But in terms of, but you can see at less than 1000 iteration, our proposed algorithm converges, while at less than 1000 iteration this converges, while here you see up to 2000, and the time keeps on increasing now. So for the infinite dimensional setting here, we consider this setting where we define the inner product to be like this and the norm to be, and here we define the function to be given by this. So this function is already established as strongly monotone and one Lipschitz continuous in the experiment. So for the demi-contractive mappings here, we define P as a projection onto some space K here, which is given by this is a half space, and PHIs, where HIs are half spaces given by this, and we define some half spaces control. These are the some functions defined in the half spaces where AIs and BIs are given by this. So for this is a simulation of the proposed method with different initial point for the infinite dimensional case. As we can see that when we take the initial as epsilon t, when we take as 1 over t plus 1 and the rest, we see that all the behavior is showing that the algorithm has convergence and takes a little much of time for the convergence. These are some selected references that we use. Thank you so much. If you have any questions and discussions.